Nuclear Physics 1. So this is the first of my nuclear physics videos, and it's about early models of atoms. So atoms were invented around 400 BC. This bloke here, Democritus, a Greek guy, suggested that everything was made up of tiny indivisible particles, and as the word tomos is to slice, something you can't slice is atomic, so tiny little particles. And for a long time people thought that atoms were very small solid little balls which were indivisible. They were fundamental particles. 1897, J.J. Thomson discovered the electron, and he discovered that you could take away these tiny negatively charged particles from atoms, and what you were left with was positive. His apparatus basically involved producing cathode rays. So J.J. Thomson discovered the electron, and he came up with something called the plum pudding model of the atom, which you should remember from GCSE. Basically saying that the atom is a ball of very fluffy, light, positive sponge, and then these tiny little negative electrons were embedded in this sponge. This model didn't last for very long because Ernest Rutherford came up with a new model, one of his students actually, a bit later on. So Ernest Rutherford and two of his students, Geiger and Marsden, did a very famous experiment involving gold foil and firing alpha particles at gold foil. A friend of his, Marie Curie, gave him a lump of radium, and he was doing experiments with radium, and he fired alpha particles at gold foil. Now at the time, alpha particles were known to be very small, very high energy, positively charged particles with a small charge to mass ratio. It was known they were about 2,000 times heavier than electrons, so like bullets, very fast moving, heavy little particles like bullets from a gun. So, excuse me, imagine firing a machine gun at a plum pudding or a piece of tissue paper. What would you expect to happen to the bullets? Obviously you'd expect them to go straight through. What happens is that most of the alpha particles do go straight through. However, a small number are deflected by small angles. A very, very small number are deflected by big angles, even more than 90 degrees. So what's going on? Well, there must be something inside the atoms which was deflecting them. Something very small, something very dense and positive inside the atoms must be deflecting the alpha particles. And Rutherford thought about it and basically came up with the idea of a nucleus. The atoms have a very small, very dense, positively charged nucleus. We know it's very small because most of the particles just go straight through and they don't go anywhere near a nucleus. Some of the particles which get close to the nucleus are repelled because alphas and the nucleus are both positively charged, and then a very, very small number collide head-on and bounce back. So Rutherford's new model of the atom, a very small, dense, positively charged nucleus, and then the electrons are in orbit around it, like planets in orbit around the sun. Rutherford did the maths and worked out, well, we knew that the size of atoms was about 10 to the minus 10 meters, the size of the nuclei about 10 to the minus 15 meters. That's 100,000 smaller. That's like, imagine a football stadium with a Smartie in the middle. Okay? Pretty soon after, neutrons were discovered, and we get to what we imagine is the GCSE model of the atom. This is an exam question which might come up. Two alpha particles approach a gold nucleus. Draw an arrow from point X on the path of particle A to show the direction of the force acting on it due to the nucleus, and complete the path of particle B. I'll give you a second to have a think about that, and the answer is like this. Okay, so obviously the force on X is repulsive, so it's away from the nucleus. The path of B, well, the particle gets closer to the nucleus and it deflects more. Because it gets closer, there's a bigger force acting on it, and it's deflected. Okay, there is a calculation to find something called the distance of closest approach that you should know, and if you look at my video on non-uniform electric fields, you'll find it on that.